Hello, my name is Emmanuel Etukudo and I'm currently taking Physics 2211 at Georgia Tech, and this is my lab report on oscillations. This class discusses four key topics, the first being Newton's second law, which states that an object's acceleration is dependent on a net force being applied to an object and the mass of that object. Spring and gravitational forces determine how much force is used on an object in relation to the spring or the gravitational body nearby. Potential energy is the energy stored up in an object, and the energy principle states that energy can neither be created nor destroyed but may be transferred from one form to another. The purpose of this lab was to investigate the motion of a mass oscillating vertically on the spring and compare the results of a computational model. On the left, there is a model of a string in its compressed equilibrium and stretch state with a mass hanging off it, which is similar to the experiments we'll be carrying on, as the system is the object itself, with the surroundings being the spring and the earth. On the right, there are a few equations which we'll be using today in our computational model. I used this video provided to us and plotted the x and y positions in tracker for each frame. I chose my axis such that the positive x points to the right and positive y points upwards. My initial conditions for my computational model. I first set the mass of the ball and its initial position and velocity vectors. I then defined g, the acceleration due to gravity close to Earth's surface, the spring constant which I calculated using the period of oscillation in the y direction, and L0, which is the relaxed length of the spring. Finally, I computed the system energies using the formulas from the previous slides and set the total energy to be the sum of these individual energies. In the calculation loop, I calculated the force due to gravity and spring force using the formulas from before and set the net force equal to the sum of these two forces. I then applied the momentum principle using the two formulas shown here to update the ball's position and velocity. I then updated the spring and recalculated L hat and S, the spring displacements, from its equilibrium position. And finally, I calculated the change in each form of energy using the same equations from the previous slide. For the results, here we see the change in energy versus time graph. The gravitational potential energy and the spring potential energy more or less switch back and forth, as seen by the fact that they oscillate roughly opposite to each other. However, let's not forget about the kinetic energy, which also oscillates as the mass speeds up and slows down during its motion. What's most interesting in this graph is actually the orange line, which plots the change in total energy. This line is more or less flat and on the x-axis, suggesting no change in total energy for the entire motion of the mass, and we'll be coming back to this in the last part of the lab. Let's take a look at the second and third graphs. In both graphs, the predicted and observed motion line up pretty well. However, for the x position versus time graph, we see that the two lines deviate a bit later for time values. This could be down to the fact that I calculated the spring constants using the time period for oscillation using the y data, which may not line up perfectly with the x position data, thus resulting in this discrepancy. I'll discuss a potential solution to this in the last section of the lab. For the y position versus time graph, the data lines up pretty well except the maximums and minimums. This could have happened if I overpredicted the initial displacement in the y direction. Is the energy principle satisfied? Well, from earlier, we said that no work is done in our system, which includes the spring, mass, and the earth. By the energy principle, the work done is equal to the change in total energy of the system. If no work is done, the change in total energy should be equal to zero, which is exactly what we see here with the orange line in the previous graph. Therefore, the energy principle is satisfied. I mentioned earlier the discrepancy in the observed versus predicted data for x position. This could be solved by calculating the time period for oscillation in x direction and using that value to calculate the spring constant and using the computational model. I've calculated the two oscillation time periods and it is evident they differ rather significantly. This has quite a major effect on the results as we use the time period to calculate the spring constant, which is used alongside other variables to predict the mass's motion. What we could do is find an average period of oscillation and use that value in the computational model, or we could use different time periods of oscillation in the x and y direction and hence have different spring constants for motion in different directions. However, this will require more advanced physics concepts and a better understanding for the spring force, and is probably beyond the scope of